Okay, we'll start. We are looking at the energy equation, and I'll start with a bit of this is the energy equation applied along with the Reynolds transport theorem. So, here if you look at it, this part is the first law of thermodynamics, valid for a system, and this part is Reynolds transport theorem with B is equal to E and beta is equal to small e. Small e was the specific internal energy, and this is equal to E internal plus E kinetic plus E potential and the symbols for internal energy we use. Specific kinetic energy will be speed square by 2. Potential energy due to gravity, again specific, will be Gz. E others will be if there is any other form of magnetic, nuclear, chemical, anything else, and at least for our part we will neglect. So, specific energy will be U plus V square by 2 plus Gz. Now, we have already discussed this. dq by dt was rate of heat addition to the system, and dw by dt was rate of work done by the system. And here gravity, rate of work done against gravity will not be included because it has been counted in potential energy. As you know, either you can say work done by gravity when you use the work energy principle, or you say change in potential energy. So, that has already been counted. And then we started looking at the details of dw by dt. And the first type of work, so this is, here we said the first type was if this is a system and there is some sort of a shaft if the control volume cuts through a shaft which either provides or extracts energy from the system. And this is the sort of interaction which the system will have, which gives you the useful work. Either you provide energy to the fluid or you extract energy. And the rate W dot S. So, what we will do is we will define the rate of work in this process as W dot S, which means the rate of shaft work. And the whole purpose of this is this isolates the machine element which is providing or extracting work from or to the system. And here we gave some examples. Example was, if there is a pump, it provides energy to the system, or does work on the system. And in this case, W dot pump, because this is being work done to the system, will be negative. Energy is being provided to the system. Or it could be a turbine type of machine which extracts energy and then W dot turbine will be greater than 0. So, one of the work which comes because of interaction with the system, which the system does with the outside, is through this W dot S. And this will be an important component of work. And actually, sometimes we will assume the fluid is inviscid. But even if we assume inviscid, actually for an inviscid system flow, there cannot be any shaft work, strictly speaking, because the work is done only through viscosity. Whatever energy comes to the fluid is only because there is some viscous effect, otherwise the body will just keep on rotating without any restriction. So, that is in some sense an engineering way of clubbing all the work extraction through the external surroundings in W dot S. Now, in addition to this, we also have surface forces acting on the system. Now, these surface forces will act on the boundary of the control volume. Now, what sort of surface forces will be there? So, we can divide them into two parts: pressure we have divided the surface forces into, or surface forces per unit area into two types of term: pressure and viscous forces. So, now when we talk of, let us look at rate of work done by the pressure. Now, this will be, let us say if this is the surface, then this is N, let us say there is an inflow, then what we find is rate of work done by pressure is equal to P times dA times, if I look at the magnitude, P dA is the force, V normal, that means look at the normal component of velocity. So it is P has its direction, I have to take a dot product with V. So that will give me P dA times V normal. That is the magnitude. Now let's see. So rate of work done on the system by pressure, this will be equal to P dA because pressure points always points inwards. So the rate of work done on the system, suppose there is fluid coming in, it will be P dA V inflow, the normal component of it. This is rate of work done on the system. So this will be equal to this, I can write it as minus P V dot N dA because N points outwards. So now rate of work done by the system, this will be equal to, so firstly work done on the system has a minus sign, so work done by the system will be opposite, and then we have to integrate it over the entire surface. So I will put this as integral over the control surface P times V dot N dA. And this I can write it as integral over the control surface P by rho. Like to write everything in terms of mass flow rate. So we write it as P by rho times rho V dot N D. Okay. Now notice on portions of the control volume which is adjacent to a solid boundary which is not moving, this term will be 0 because there is no flow crossing. So this will count only at the crossings where the flow is entering or leaving. If the flow does not leave on all those parts of the control surface, this term will be 0. So we have to count for this term only at the inlet and the outlets. Okay. So this is the work done by pressure. Next, if we try to look at work done by the other shear stress terms tau. Now this includes shear stress and non-isotropic part of normal stress. Because remember in fluid mechanics, we did not divide into normal and shear stresses. We defined the stress tensor into pressure and deviatoric part. So deviatoric part includes all the shear stresses and the non-isotropic part of the normal stresses. So now the work done by viscous forces on the system will be minus shear stresses dotted with V dA. So now let's try to think, if this is our system, there's a inlet and an outlet. and if this is our control volume, then firstly viscous work is equal to 0 on those parts of the boundary where velocity is 0, tau dot v will be 0. So there is no viscous work on those parts. On those portions where fluid crosses the control volume, so that means we are talking of let us say this is the inlet. Now here if tau acts, shear stresses will act in a plane perpendicular to n, V inlet and if we make the cut such that V inlet is parallel to n, then when we take tau dot V, it will become 0 because tau is in a plane which is perpendicular to the velocity. So in this, if we make this cut like this, then tau dot V is equal to 0 for shear stresses. So only contribution will come from non-isotropic part of the normal stress. The normal stress may still have some non-isotropic part and that dotted with V will not be 0. But in most cases when we talk about this, we will consider the viscous work as 0. And of course, the more important part is those certain parts of CV where the control surface cuts the shaft. See, there the work done is important, but this has been accounted in W dot S. So we say in most cases, viscous work, particularly when you have a solid surrounding, is nearly 0. Now, are there cases where viscous work cannot be neglected? So here, let's see our control volume. So let's consider an expanse of fluid. And in this, what I do is, I choose two streamlines. a streamline 1 and a streamline 2. The flow is going, that means I just showed the dotted line as a reference that everything is fluid, and in the fluid I choose 2 streamlines, and suppose if my control volume if the control volume is chosen as the dotted line. So now, so this is one on surface of streamlines. One and two, the fluid is not crossing, but if I look at the viscous work on surface 2, it will be tau dotted with V. Now streamlines, there can be no normal component. So the velocity component is only a tangential component. So tau dotted with V on 1 and 2 will not be 0 if viscosity is important. Do you see that? So in a control volume like this, if I choose, so here now on surfaces 1 and 2, if viscosity is not negligible, then work dot viscous cannot be neglected. If shear stress is substantial and there is a velocity, so tau dot V is there on surface 1 and surface 2. If I look at the two perpendicular surfaces, there will be no tau there. If I choose the cut perpendicular to the velocity, there will be no tau dot V there. But on surfaces 1 and 2, if viscosity cannot be neglected, the viscous stress will be 0. But if we assume inviscid flow, that is mu is very small, then on the streamline surface, the viscous work can be treated to be 0. Okay. So now, having combined all this, the total work done can be written as W dot CS plus integral on the control surface P by rho times rho V dot N dA minus integral on the control surface tau dotted with V dA, and this part we will neglect. The viscous work will be neglected. So therefore, now when I write the total this thing, the energy equation for a control volume, I have Q dot minus W dot is equal to d by dt of so this I will write it as Q dot minus W dot S So I have clubbed everything. W I have written as minus W dot S minus integral of P by rho V dot NdA is equal to partial by partial T. The right hand side comes from Reynolds transport theorem. And for small e, I have written all the three components. So this is where we are now combining. So now what I can do is I can take the P by rho term and combine it with the last term on the right hand side, because I have a surface integral rho V dot NdA. So this becomes therefore, so Q dot minus W dot S, this becomes d by dt of volume integral of u plus v square by 2 plus gz dv plus integral over the control surface P by rho plus u hat plus v square by 2 plus gz into rho v dot nd. U plus v square by 2 plus G. Okay. So this is the full form of the energy equation with the terms, and you can see where I am heading to. Where am I heading to with this? If you look at the last term, P by rho plus V square by 2 plus GZ. So I am heading to the well-known Bernoulli equation. So let's see now. How do we, and again you may have realized the way we are doing things, we did it for mass balance and all, that all those equations which we know are actually special forms of something which is very more general. And in particular about Bernoulli equation, I will tell you it is one of the most misused equations in fluid mechanics, because we keep on using it even in conditions where it is not valid. So therefore, it is important for us to see what is the Bernoulli equation and how does it get derived from here. So first let's look at a case. We talk of steady state flow and fixed control volume. If we have steady state and fixed control volume, then what happens? What simplification can we make? Which of these terms will go to zero? बताइए. The volume integral term, because I can take the d by dt inside if it's a fixed control volume, and because the flow is steady, then things will not change with time. So therefore, if it is a steady state and fixed control volume, this implies the d by dt of the volume integral term, this is equal to 0. Okay. So this is the first assumption. Secondly, we say we choose a control volume with one inlet and one outlet, and both inlets and outlets have 1D flow. Even if they don't have 1D flow, then basically what we are going to do is this term rho v dot NdA integral. Now I'm not on the inlet or the outlet, we will write it as m dot. So if I say integral over AI, I will call it as m dot I. And actually you can generalize this even if there are more than one inlets, more than one outlets. Then all you have to do is you have to write it as m dot I for each of those. Okay. So this is the second thing which we will have. And then if you have to use it in the energy form, then internal energy plus P by rho is also defined as another thermodynamic variable called enthalpy. So, this is H is the specific enthalpy, and then what we will get is Q dot minus W dot S is equal to minus M dot H1 plus V1 square by 2 where 2 is the outlet, 1 is the inlet. And here, because there is one inlet, one outlet, we have already used mass conservation. M dot is common. I am not saying M dot 1, M dot 2. How will you generalize this if there are more inlets and outlets? Then it will become minus M1 dot, minus M2 dot, minus M3 dot if there are 3 inlets. And if 4, 5, 6 are outlets, then plus M4 dot, M5 dot, M6 dot, and corresponding terms with the corresponding subscripts. So, this is how one can then expand this. So, but for one inlet and one outlet, which is a common situation, we get this equation. So, this is the energy equation Now, what one can do is we can divide each term by m dot. In this energy equation, we can, because there is an m dot on the right hand side. So, then what we have is the first term q dot by m dot, we can write it as small q. Now, there are two dots. So, the rate is divided by another rate. So, that derivative with respect to time in some sense goes away, and this is heat transfer to the system per unit mass. Similarly, Ws divided by m dot, this one can write as small ws or shaft work per unit mass flow. So, or per unit mass flow, actually this was also per unit mass flow. And dimension of each term is that of V square. So, that means we will get equation like Q minus Ws is equal to minus of H1 plus V1 square by 2 plus GZ1 where H1 is the enthalpy. Did I have? Okay. And I can also write it as minus of U1 plus P1 by rho plus So, we first divide it by m dot, and this is sometimes further divided by g. If you now divide by g, then dimension of each term, this will be dimension of V square divided by G. And what is dimension of V square divided by G? That dimension will be length. V square is equal to 2GS. So you directly know the dimension of V square by G is length. And this is called, referred to as head. In hydraulics and in fluid mechanics, you will see all these terms as referred to as head. You must have heard head of a pump. Have you heard that the pump has a head of 10 meters? Otherwise, you will see these terminology when you come across pump specifications and turbine specifications, then they are given as a head. That means so many meters. So the head basically comes from here, and what we have is P by rho G, the term which will come from pressure. This is called pressure head. V square by 2G, this is called kinetic or the velocity head. Z is called the elevation head. And W dot S divided by M dot G. This is the head due to shaft, and you will have a head turbine or a head pump. Head turbine will be greater than 0. Head pump will be less than 0. So one can then define all these heads. So sometimes when you are using the energy equation, then you may have a head term and you can then use this. Now when you use it as an energy equation, either if you assume temperature to be constant, then U1 hat will be equal to U2 hat. And then you will work out the equation. Or if you are looking at enthalpy, if they are given, then you will know H1 and H2, you use that. So this is how one can use the energy equation, look at all the inlets, outlets, etc. Now let us look at a special control volume. And this control volume, we call it as a stream tube. What this means is, this is in a fluid flow, I take a small ring. So in the expanse, so that means once again, it's something like so take a small ring in fluid. Now, from all the points on the surface, this is a closed ring and there are streamlines which pass through every point on the surface of the ring. Okay, you follow those streamlines. So the control volume consists of the ring and the streamlines, and you follow the streamlines. So on the other end, also you will have a ring. Obviously, the shape of the two ends may not be the same. So it's a streamline following from each of the points on the surface, and this is what we call as a stream tube. So this is our control volume, which is a stream tube. That means we choose a closed ring and just follow the streamlines, and we can cut it anywhere on the side too. We are starting from this point and going. Now here on this control volume, so let's say this is 1, this is 2 and this is the surface. So now I am using 3 for the surface. Okay. So now let's make the following assumptions. We assume incompressible flow. We assume steady flow. So if we assume steady flow, then the streamlines will not change. So this control volume will be a fixed control volume. If the flow was unsteady, then the streamlines would have changed with time. But because it is steady flow, they will stay as it is. So it's a fixed control volume. Third assumption, which is very important, we assume inviscid or frictionless flow. Now, because of steady flow, now the control volume becomes fixed CV with steady flow. Because this is inviscid, that means viscous work done on the surface 3 as well as the remaining part of the non-isotropic work on 1 and 2 will be 0. So by assuming inviscid flow, all this has been. Then fourth, we assume no shaft work between 1 and 2. And the fifth assumption, no heat transfer between 1 and 2. Okay. So we have made so many assumptions. What was our equation? Our equation was this. Now, on this control volume, the way we have chosen, there is only one inlet, one outlet. So we will use this form, the one inlet, one outlet. Q dot has become 0. We have assumed no heat transfer, no shaft work. So that also becomes 0. Steady flow with a fixed control volume, d by dt is 0. Now there is one inlet and one outlet. So therefore, what we are left with finally is, so this will imply m dot times u hat plus p by rho plus v square by 2 plus gz at 1 is equal to m dot times u hat plus p by rho plus v square by 2 plus gz at 2. And because there is no heat exchange, u1 hat is equal to u2, and this gives us v square by 2 plus gz plus p by rho at 1 is equal to v square by 2 plus gz plus p by rho at 2. And in the limit, radius of the stream tube goes to 0. If the radius of the stream tube goes to 0, what happens to the stream tube? It becomes a streamline. If the radius of the stream tube is made smaller and smaller, this will imply the stream tube becomes a streamline. And so the equation is valid only for 2 points lying on the same streamline. So this becomes, we have said the fifth assumption. The sixth assumption becomes points 1 and 2 have to be on the same streamline. And this equation is what we call as Bernoulli equation. There are actually three Bernoullis, grandfather, father and son, who talked about this. I think one of them is ये तो थोड़ा ज्यादा हो गया यार, मतलब क्या ऑटो नहीं मिला, बस नहीं मिली, ये तो थोड़ा सा ज्यादा हो रहा है. अब तो मौसम भी अच्छा हो रहा है, गर्मी भी हो गई, सर्दी भी नहीं रही, मतलब दिस इज. So this is what Bernoulli equation is. That means if you are using, now realize we are talking of integral flow analysis. But the way we have defined Bernoulli equation, this is to be used between 2 points. And basically what it is going to do is, it will give you a relation between pressure and velocity. That is what Bernoulli's equation gives you. So this equation in integral flow analysis will be used between 2 points. So in that sense, it is not on the whole control volume the way we are doing mass balance. And this will give a relation between P and V, which is the speed. So now once again, at the risk of repetition, for Bernoulli's equation to be valid, there are 6 assumptions. One is the flow should be incompressible. It should be a steady flow. So that means sometimes in certain reference frames, flow is unsteady. But if you change your reference frame, flow becomes steady. So therefore, Bernoulli's equation will be valid only if the flow is steady. In the unsteady reference frame, there is an unsteady form of Bernoulli equation. We will not be able to do it in this course. And it can be done. And we can show that if we change the reference frame, we get the same pressure if we use the unsteady form for the unsteady case and steady form for the steady case. Third thing, which is another very important assumption, is that you have to assume that viscosity is negligible. Mu is 0. It has to be frictionless flow. Then of course there is no shaft work, otherwise energy exchange is taking place, and no heat transfer. And then comes the sixth point, that flow has to be between 2 points on the same stream. Now this we may be able to show that this can be relaxed if in the flow if the velocity field is such that if del cross V is 0, then the same streamline condition is not needed. And right now it is difficult for me to explain it, but the way we can look at it is, if I look at the differential form of the velocity equation, then I can get an energy form from there also. And when I look at the energy form from there, then I get this expression. And in some sense, what you can look at is that this quantity P by rho plus V square by 2 plus Gz, if I call this as, let's say, Bernoulli's constant, B. And suppose in a flow, if at a start or at all the streamlines, this value is the same. Now, when you go and follow the streamlines, at all later points in the flow also, the value will be the same. But if it is the same for all streamlines, then it will be the same everywhere in the flow. And that is how this condition del cross V ensures that. So, the sixth condition, in view of this, condition 6 is either 1 and 2 on the same streamline, or del cross V is equal to 0. And so, if this is the flow, then as we said, we can apply Bernoulli equation between A and B and between C and D. But in general, not between वो क्या हो रहा है वहां पे? ये लोग क्या, ये क्या तमाशा चल रहा है क्या यहाँ? क्लास के बीच बीच में उठ के कहाँ जा रहे हो तुम लोग? यही लोग लेट आए थे ना शायद? तो पूरे क्लास को तुमने तमाशा बना रखा है। पहले लेट आओ, फिर जहां मर्जी इधर उधर घूम रहे हो। थोड़ा डांस भी कर लो यहाँ स्टेज पे आके। आई थिंक इट विल बी गुड, विल ऑल एंजॉय। So, as we said, if there are different streamlines, and the point I was trying to make is, if Bernoulli's constant for A and C are the same, then actually you could apply Bernoulli between A and D also. But notionally, you should always apply it on the same streamline. And see, sometimes what we know is, if the flow is curved, then partial P by partial N direction, they will be equal to rho times A. There is, so if we have curved streamlines, if we have things like this, then we know the normal acceleration is not 0. What will be the normal acceleration? It will be equal to even if the velocity is constant, in case of curved streamlines, the normal acceleration will not be 0. And what we have seen is minus gradient P by rho is equal to is equal to, or minus grad P is equal to rho A. So even if we have flow with constant velocity and curved streamlines, in the normal direction pressure changes. And this pressure change, if the velocity is constant, Bernoulli's equation, when you apply it between 2 points A and B, which are not on the same streamline, you will not get this. So Bernoulli's equation, the pressure change in the normal direction comes from something else. It comes from the curvature of the streamline, not from Bernoulli's equation. And this is one common mistake which people do, that you apply PB minus PA cannot come from Bernoulli equation, but will come from so this pressure distribution is going to come from this equation, the governing equation, not from Bernoulli equation. And this is the mistake which often people make, that they apply Bernoulli equation in this. Now, let's see how Bernoulli equation can be used. Before we will talk of some situations where it cannot be used, but some examples. And now we have covered the entire theory for integral flow analysis. There will be different type of problems. So some guidelines for integral flow analysis problems. The first rule is, whatever problem you solve, mass balance has to be satisfied. And many of you later on may use CFD also, which means we use computational fluid dynamics to solve the differential equations. And there also often a lot of programs go wrong because mass balance is not satisfied. You are creating or sort of removing mass, and that creates a lot of havoc in all the calculations. So mass balance will have to be satisfied. Either the data given will be such that mass balance is satisfied, otherwise one of the velocities, either at the inlet or the exit, will not be given, and that you will get from mass balance. Secondly, then we draw the free body diagram of the control volume, which means we first draw the control volume and show all external forces on the control volume. And then, and one important part of doing this is show directions of coordinate axis. So if you draw your control volume, you should also show where your x and y are. And the reason for that is, when you use the force equation, then there will be a component of V and a component of V dot n. So component of V will depend on how you are choosing your X and Y. In certain problems, you may decide to choose Y pointing downwards, that's fine. But then you have to clearly show your directions on the figure and then work out. And typically, Bernoulli equation will be used to find pressure at some location. And where will you use this pressure? This pressure will be used in the surface forces on the control volume. So either the problem may be direct, you will be asked to find the pressure at some location. Otherwise, and for pressure again, please go through my notes earlier 2 lectures before, where I said there are 2 exceptions. If the flow is coming out as a jet, then the pressure is P atmospheric in the jet at all points. And if it's a one-dimensional flow and it is with gravity, then we assume pressure is hydrostatic at any cross section. So there you don't need Bernoulli's equation, but otherwise Bernoulli equation will be used to find pressure at this location. So now let's take one example. There is a tap of fluid, beaker of fluid, in which a tube is put, and the other end of the tube is somewhere which is at a level lower than this. Has anyone seen this situation anywhere? किसी ने देखी है ये कभी कुछ यूज किया है इसको? हाँ, but have you used it when petrol चुराया था कहीं? But normally this is used when you have to steal petrol from the tank of a car, from the tank of some scooter, or not steal maybe, you're taking it out in a bottle from your own scooter. So then what do? You start, take the tube to a level below the level of the tank, you suck the petrol out and you leave it and it continues to flow. So now, here what is given to us is, this is the free surface and this total height is, let us say, h2. This height is h, and we are asked to find the flow rate through the pipe. Okay. Now here this becomes a direct application of Bernoulli equation. Now what we know is, let's call this point as 1, this point as 2, the highest point as 3, and the exit is 4. Okay. Now we have to find the flow rate through the pipe. How will we, between which points will we use Bernoulli equation? We'll assume the flow is inviscid and all that, all the assumptions will be, flow is steady, that means the flow has been going on and the level at which this is going down is very low, so that we can assume that capital H is very slowly varying with time. Now if I apply Bernoulli equation, what do I know at the start? Do I know pressure at any point? Do I know P4? because the flow is coming out to the atmosphere, P4 is P atmospheric. Is that clear? Now, which other points do we know the pressure a priori by just looking at this problem? Do I know P1? What is P1? Pressure on the surface of the tank. It is also P atmospheric. Do I know P2? So these two things are known to me. Now the question, and this is where the common mistake is made. Do I know P2? Is P2 P atmospheric, or is it equal to P1 plus rho g times H2 minus H? Or whatever, rho g times this depth, which we don't know. Well, we can't say anything because this is not statics. So, as far as P2 is concerned, we do not know anything. But what we say is that any flow which is going out from 4, the streamline of that has to start from 1. That means any flow which is going out, the streamline has to start from 1. So what we do is we apply Bernoulli equation on a streamline between 1 and 4. So that is what you will do is apply Bernoulli equation on a streamline between 1 and 4. So P1 by rho plus V1 square by 2 P4, this also is valid, but we'll apply between 1 and 4. So, sorry, so we will make it as and P1 is equal to P4 is equal to P atmospheric. And for V1, we will use the continuity equation. V1 A1 is equal to V4 A4. And assuming A1 is very large, we can assume that V1 is nearly 0. Otherwise, in other situations, you will use V1 A1 is equal to V4 A4, and that will give you a relation between V1 and V4. So here, then we assume V1 A1 is equal to V4 A4, and since A1 is much bigger than A4, we will assume that V1 is nearly 0. So from here, we can get V4. Once I get V4, then we will use continuity equation and say assuming this tube has a uniform area, V2 is equal to V3 is equal to V4, and then I can get pressure at different locations. Okay? So this is how this problem has to be done. And similar problems, when you come across, you'll have to do it using this way. Apply Bernoulli equation if both the velocities are not known, or if both pressures are not known, one of them. So maybe some assumption like this has to be made, and that will give you V4. Otherwise, you will get a relation between V1 and if areas are both known, then also you can work out, you can put this and use Bernoulli equation, and that will give you both V1 and V4. Here we assume V1 to be 0. Okay. If both the areas are fully known, then you can also see how much error we are making by assuming V1 to be 0. Let us say the tank is 10 meter square and this is 1 centimeter or something, the diameter. You can work out some scenarios and see that this is going to be valid. Okay. Now, what happens is, you can show here the lowest pressure is at P3. The point where the height is the most, that is where you get lowest pressure. And sometimes what happens is, in flow of a liquid, if pressure becomes low, it can become equal to the vapor pressure, that is, the fluid will start or that is the liquid will start converting to the gas. When this is a thermodynamic process, if the pressure in the liquid becomes low, then it can start becoming converting to a gas, and this phenomena is called cavitation. And you see cavitation, the onset of cavitation, you see it by that there will be bubbles will start to form. And generally cavitation is best avoided. If there are bubbles, let's say, in flow around a turbine, then the bubbles start hitting the turbine blades and they cause more erosion. So therefore, in general, normally we would like to avoid cavitation. So we would avoid, if there is a flow of liquid, the pressure we would like to keep such that it stays below, above the vapor pressure. It does not go below the vapor pressure. Now, in certain other problems, let's say if there is a fan, if you have a control volume like this, which has a fan which is a part of the control volume, then clearly you can't use Bernoulli equation between the inlet and the outlet, because energy is being provided by the fan to the flow. So here let's say this is 1, this is 2. We cannot use Bernoulli equation on a streamline between 1 and 2. But if we divide the domain into subparts, then if other conditions are satisfied, we can apply Bernoulli between 1 and 3. And we can apply it between 4 and 2. But we will not be able to apply it between 3 and 4. So in this case, BE can be applied between 1 and 3, between 4 and 2, but not between, but between 3 and 4, we can still use continuity equation and the force equation, provided we do proper force balance. So basically Bernoulli will be done to find P3 and P4 given P1 and P2, and then we will do a control volume analysis on 3, 4 with proper pressures, etc., and work out the situation. Okay. So this way then one can do. Now also there may be a situation like this, there's a problem in the book also. Flow in a sort of a fork. That flow is coming in from one, it gets divided into 2 and 3. Now here you can use Bernoulli equation on a streamline between 1 and 2 and between 1 and 3. You choose a streamline going from 1 to 2, you can apply Bernoulli equation. You choose a streamline going from 1 to 3, you can use Bernoulli equation. So effectively it becomes you are using Bernoulli between 2 and 3, but notionally that is wrong. There is no streamline from 2 to 3. But if you use Bernoulli equation, it will give you the right result, but not conceptually. Okay. And one last thing, if not all, that often you have situations like this, when there is flow, then if there is mixing, so if the flow is mixing in general, if there are straight streamlines, you can use Bernoulli equation. But if there is mixing, then mixing will lead to losses of energy and you will not be able to find a proper streamline. So you cannot use Bernoulli equation. Also, in general, near the boundaries, viscous effects are important. So we cannot use Bernoulli equation. Otherwise, for integral flow analysis, we will be using Bernoulli equation. Now, one homework, okay, खत्म कर दीजिए.